Welcome to the deep dive. Our mission today is, well, it's an exploration into humanity's ultimate existential dilemma.
It really is. We're looking at some high-stakes astrophysics papers on the fate of the cosmos.
And we're pairing those with data from cutting-edge exoplanet discoveries and the
Yeah.
core engineering philosophy behind the quest to colonize Mars.
Yeah, this deep dive is really tailored for you, the learner, because we are trying to synthesize two massive and often, contradictory ideas.
Which are,
On one hand, you have the vast impressionable certainty of the universe's eventual demise. It's just physics.
and on the other.
The hyper-focused, incredibly urgent human response that aims to ensure consciousness survives, regardless of what that cosmic clock is doing.
So we're pulling on three huge interconnected threads today. First, we're looking at the inevitable end scenarios for the entire cosmos. We're talking the big punch, the big rip, or that long, cold silence of heat death.
Then we zoom way in. We're going to look at the elusive search for life elsewhere, specifically at anomalies around an interstellar object called 3ILS.
And the really tantalizing biosignatures they might have found on the exoplanet K2-18b.
Exactly. And finally, we pivot to what you might call the human imperative, the blueprint for a multi-planetary civilization.
We'll be dissecting this unique first principles thinking that's driving the whole effort.
Treating space colonization not just as, exploration for its own sake, but as the only reliable extinction insurance we have.
So it's the story of existential dread met by relentless, and I mean relentless, engineering genius.
A perfect summary.
It's time to start unpacking this. Let's begin with the ultimate cosmological question. What are the governing rules that dictate the fate of, well, everything we know?
The universe's destiny really hinges on this ongoing, you could say, intergalactic conflict between two opposing forces.
Okay.
On one side, you've got gravity. This is the reliable workhorse of the cosmos, always pulling mass together. It's what forms stars, planets, galaxies.
And on the other side, the mysterious and much more dominant force that we call dark energy.
Right. And when dark energy was discovered back in the late 1990s, it completely changed our understanding of the universe.
Because it revealed the universe isn't just expanding.
It's accelerating. And that
Yeah.
acceleration is everything. Before that discovery, most cosmologists just assumed that gravity would eventually slow the expansion down.
That seems logical. Enough stuff should eventually act like a brake.
It does seem logical. But then they looked at Type Ia supernovae. These are sort of cosmic yardsticks because they burn with a very predictable brightness, and they saw distant galaxies moving away from us faster than they should be.
So the universe wasn't hitting the brakes at all. It was slamming on the gas pedal.
It was. And our sources describe dark energy as behaving almost like it has negative gravity. It's not pushing objects through space. This is the key part.
Okay, what is it doing then?
It's creating more space between objects. It's a vacuum energy, a property of space itself, that just exerts this repulsive pressure.
So for the last, 20 years, the consensus has been that this acceleration just continues forever.
Yes, leading to what's called the big freeze. That was the standard model.
But there's always a but in cosmology, isn't there?
There is. New cosmic observations have introduced this major theoretical possibility that dark energy might not be constant.
It could be changing over time.
It could be weakening. There are some models based on analyzing the latest supernova data that suggest it might behave less like a static cosmological constant and more like a dynamic field that's, running out of steam.
And that tiny sliver of weakening is the whole story.
It's the crucial point. Because if that repulsive force begins to fade, even slightly, then gravity, the attractive force, could start to regain the upper hand.
And that opens the door for a non-eternal expansion. The universe could actually halt its outward journey and reverse course.
It's a huge speculative leap, of course.
Yeah.
We're extrapolating from a force we still fundamentally don't understand.
But it's absolutely critical for framing these three big scenarios for how it all ends.
And the first one, if that weakening force hypothesis is correct and gravity wins, we face the dramatic, fiery conclusion known as the Big Crunch.
It's not like running a film in reverse, is it? Can you walk us through what that would actually look like over eons for some hypothetical observer?
Oh, it would be terrifyingly dynamic. Not just a simple rewind. First, expansion would cease. Then, the contraction phase would begin.
And as space shrinks, everything gets closer together.
Right. The density of matter increases rapidly. From our point of view, distant galaxies would stop redshifting moving away, and they'd start blue shifting moving toward us.
The sky would just become incredibly crowded.
Incredibly. The probability of interactions would just soar.
Stellar collisions.
They become common. Planets would be torn from their orbits as gravitational forces just overwhelm the stability of their solar systems.
Hmm.
And everything, I mean everything, heats up dramatically.
Because you're compressing all that energy into a smaller and smaller box.
Exactly. You remember the cosmic microwave background, the CMB? That faint radiation from the Big Bang that's currently just near absolute zero?
Yeah, about 2.7 Kelvin.
It would heat up intensely to thousands of degrees. It would sterilize any remaining life long, long before the final singularity.
So the end state is just one vast fireball.
One central fireball where all matter, energy, space, and time collapse back into an ultra-dense, ultra-hot singularity. It's essentially reversing the initial conditions of the Big Bang.
Wow. That's a spectacular, though, very short-lived demise.
Very.
But let's look at the more favored scientific outcome, the one that the data still points to if dark energy remains constant. Let's talk about the big freeze, or heat death.
Right, this scenario is less dramatic, but in a way, more profound. It's deeply rooted in thermodynamics, specifically the second law.
Entropy. The idea that everything tends toward disorder.
Precisely. This idea was formalized by Lord Kelvin way back in 1852. He observed that in any closed system, and the universe is the ultimate closed system, energy naturally spreads out. The system becomes irreversibly messier.
It's approaching a state of maximum disorder.
Correct. And if dark energy and expansion continue forever, it spreads matter and energy so thinly that it just maximizes this disorder. Stars will exhaust their fuel.
And then what?
Stellar remnants, things like white dwarfs and neutron stars, they'll just cool and fade. Even black holes will slowly, over unimaginable timescales, evaporate through Hawking radiation.
So the universe becomes a cold, dark void, just a thin soup of subatomic particles drifting further and further apart.
That's it. Everything approaches absolute zero. And because movement itself requires energy differentials, heat flowing from hot to cold, once that differential vanishes, the universe reaches a state of ultimate rest.
Our sources say nothing will ever move again.
It's the big freeze. A slow, silent, isolated death by entropy.
Okay, now for the third, and maybe the most aggressive scenario, the big rip. What happens if dark energy doesn't just stay constant, but actually gets stronger?
This is the ultimate runaway scenario. I mean, the violence is on a scale that's hard to comprehend. If the density of dark energy increases past a certain point, the repulsive force becomes so great that it overcomes gravity on the galactic scale. So first, galaxies are torn apart.
Okay.
Then, as the expansion accelerates even further, it starts to overcome the other fundamental forces. The electromagnetic force, the weak nuclear force, things that hold solar systems, planets, even individual atoms together.
So you're saying everything,
Right.
from clusters of galaxies down to the quarks inside a proton, gets violently ripped apart by the sheer speed of space expanding.
That is the prediction. Some models even put a date on it. A theoretical event about 22 billion years from now. It's the fastest, most violent end imaginable.
And this is important. We have to heed the scientific caution here, right? Our sources mention experts like Professor Ofer Lahav urging caution.
Absolutely. You're right to bring in that intellectual friction. Given all this terrifying detail, most of the data we have still suggests eternal expansion and the big freeze.
So why are the big crunch and big rips still given so much airtime?
Because our data is so limited. The implications are too profound to just ignore. I mean, we are extrapolating billions of years of cosmic future from a few decades of observing a force, dark energy, that makes up 68% of the universe and that we still don't understand.
So any uncertainty in that force means our models have to carry that uncertainty.
They do. We're dealing with theoretical physics at its absolute limit, which, it naturally pushes us toward these fundamental questions about reality itself.
And that discussion of cosmic constants and uncertainty, it leads us right to the idea of the multiverse, a concept that's often debated not just for its complexity, but for its scientific validity.
The critique is very robust. Many cosmologists argue that hypotheses involving an infinity of parallel universes, they often cross the line from testable science into pure philosophy.
Because they can't be falsified.
Exactly.
Right.
You can't empirically falsify them. If you propose that an infinity of universes exists just to explain the specific fine-tuned constants of our universe, that explanation requires the leap of faith.
It sounds a lot like what our sources suggest, that the explanatory power of the multiverse is kind of like invoking an unseen creator to explain why things are the way they are.
That's the essence of the criticism. It stops being a scientific prediction and starts being an untestable justification.
But sometimes the data itself seems to suggest we might need such an extraordinary explanation.
Right. Consider the anomaly that was spotted by Dr. Ranga Ramchari in the cosmic radiation spectrum.
What exactly did he find in that faint echo of the Big Bang?
He was analyzing the cosmic microwave background, the CMB, and he found a signal in the radiation spectrum that was 4,500 times brighter than anything predicted from the early universe.
4,500 times. That's not a small error.
Not at all. Specifically, it was from the time when atoms were first forming. This brightness suggested a massive, and I mean massive, influx of matter from somewhere.
How massive are we talking?
The signal was consistent with the region of the early universe where the ratio of matter particles to photons was 65 times greater than our own. A discrepancy of that magnitude requires an extreme explanation.
And Chari's most provocative hypothesis was what? A collision.
His hypothesis was that this signal could be evidence of a parallel universe dumping some of its matter particles into ours during the formation of atoms.
Wow.
Now, he was very careful. He stressed the high burden of proof. It could also just be distant, complex dust clouds. But the very existence of an anomaly like that highlights that our current model of a single closed universe might not fully account for everything we see.
This philosophical uncertainty about the nature of reality, it brings us right to the simulation hypothesis, which Elon Musk has famously embraced.
He has, and he finds it compelling as a potential solution to the Fermi paradox.
Why? How does he frame it?
He frames it as a probability problem. It's rooted in technological acceleration. He argues that if technological improvement continues at any rate, then eventually games will become indistinguishable from reality.
Or civilization will end. Those are the two options.
Right, so given that we exist, the statistically most likely outcome is that we are already one of the many, many simulations being run by an advanced civilization that reached that technological capability.
So why don't we see aliens? Because the aliens are the ones running the computer we live in. It's a very neat, if unsettling, way to resolve the paradox.
It is. But there's a fascinating counterargument from physicists that says the universe is fundamentally not algorithmic.
Okay, what does a non-algorithmic understanding of the universe mean in practical terms? How can physics defy computation?
This argument is based on mathematical incompleteness theorems. Computation, by definition, works on discrete, countable steps and values, ones and zeros.
Right.
But physicists argue that the fundamental laws of like the laws governing the continuous interaction of quantum fields, are deeper than computational rules. To get a complete and consistent description of reality, you would need infinite computational power.
Because the values in physics are continuous, not discrete, they're not countable.
Exactly. So the complexity of reality is too immense, too fundamentally continuous to be rendered accurately by a finite computational process.
The universe, therefore, cannot be a simulation because no simulator could possibly contain it fully.
That's the implication. It elevates reality from a program to something far more irreducible. And if the universe is more than just computation, then the only way to understand it is to actually observe what's out there.
Which leads us directly to the search for consciousness beyond Earth and the very strange anomalies we are starting to detect.
We move from the theoretical physics of reality's end to the immediate empirical search for life. And our sources give us two incredible examples of data that are just pushing the boundaries.
An interstellar visitor defying explanation and a distant world that might be signaling life.
Let's start with 3ILLs. It was a comet-like object that passed through our solar system, and it fueled this really intense comet or probe debate.
Right, because astronomers initially flagged it as an interstellar comet, but its behavior just didn't add up.
It didn't. And Avi Loeb, the UFO researcher, has been very vocal about what he calls the scientific arrogance in immediately dismissing this anomalous data.
So what was wrong with it, chemically and physically?
Chemically, it was bizarre. When the object passed near the sun, the analysis of its coma, that's the dusty cloud around its nucleus, showed high concentrations of nickel and iron atoms.
Which shouldn't be there.
Well, on a typical comet, those elements are locked inside silicates. But here they were observed vaporizing freely. And crucially, this was happening at extremely frigid distances from the sun, where the heat shouldn't have been enough to sublime these heavy elements.
So it suggests the object was made of something non-standard, maybe highly reflective or even metallic.
Potentially. And then physically, the propulsion was strange. Comets propel themselves via outgassing, jets of gas, which creates a random asymmetrical push.
But 3I Atlas jets weren't random.
Not at all.
Yeah.
The object displayed a highly symmetrical pattern in its outgassing jets. and they were observed to precess, meaning they spun slightly, but maintained this unusual rotational stability every 7 hours and 45 minutes.
Whereas normal cometary outgassing is chaotic?
Sporadic and chaotic.
Hmm.
This regularity and symmetry led some to question if they were observing a natural process or something engineered. A controlled mechanism stabilizing rotation, which, well, we would describe that as controlled propulsion.
If it is artificial, the implications are just staggering. We would have seen technology from another star system.
And that leads to the final and really unsettling layer here, the secrecy angle.
What about it?
Loba suggests that the CIA's decision to classify interstellar files might be a calculated effort to prevent a black swan event from triggering mass panic.
That's a huge claim. Why would confirming alien technology be a black swan event that triggers mass panic instead of just an amazing scientific breakthrough?
Because a black swan event is defined as a highly improbable event with catastrophic consequences. If we confirm that a foreign advanced civilization is capable of sending engineered probes across interstellar distances, the implications aren't just scientific.
They're geopolitical, military, societal.
Everything. It changes our entire defense posture, it alters the perceived scarcity of resources, and it potentially forces a complete societal restructuring based on the realization that we are technologically inferior.
So classifying those files might be an attempt to manage that potential disruption until a strategy is developed.
That's the theory. It speaks volumes that the discussion around evidence for aliens immediately pivots to questions of security and social stability.
Okay, let's move from possible engineering to possible biology. Let's talk about the discovery on K2-18b.
K2-18b is a sub-Neptune exoplanet. It's about 8.6 times the mass of Earth, and it's orbiting a red dwarf star. The important thing is that it sits in the habitable zone.
Meaning liquid water could exist on its surface?
Could, yes. Its atmosphere has been a key target for years.
I remember Hubble struggled with it previously. What did the James Webb Space Telescope, JWST, do differently that allowed for this potential breakthrough?
Hubble's instruments had a hard time distinguishing between the specific absorption bands of methane and water vapor. It's very difficult at that distance. But JWST, with its advanced mid-infrared instrument, or MERI, it provided the spectroscopic resolution needed for a real deep dive into the atmosphere's composition.
And what JWST found, these were the extraterrestrial smoke signals. Methane, carbon dioxide.
Which are often the building blocks of life, yes. But the real headline grabber was the potential detection of dimethyl sulfide, or DMS.
And DMS is fascinating. On Earth, where does it come from?
On Earth, it's a volatile organic compound that is overwhelmingly produced by living organisms, specifically marine phytoplankton. When they die, DMS is released into the atmosphere, where it plays a role in cloud formation.
So finding DMS in an alien atmosphere is a very strong prediction for a biosignature, a chemical indicator of life.
It is. The sources also mentioned that DMS and DMDS, that's dimethyl disulfide, they have overlapping spectral features.
And are both of those considered biosignatures?
Yes. DMDS is also a significant biological byproduct. The data from JWST showed features consistent with this whole chemical family. The key question, though, is how reliable is that detection?
Right. This is where we need to unpack the concept of statistical significance. The detection reached 3 sigma. For those of us who aren't astrophysicists, what does 3 sigma actually mean, and why isn't it a confirmation?
So sigma represents the standard deviation. It's a measure of the probability that your result is just due to random chance or noise in the data, rather than a genuine signal.
Okay.
A 3 sigma detection means there is roughly a 1 in 370 chance that the result is just random noise, which is good evidence, but it's not definitive.
So 3 sigma is compelling, but it still leaves a lot of room for reasonable doubt.
Exactly. For something to be considered a confirmed breakthrough discovery in physics, like the Higgs boson or gravitational waves, the threshold is 5 sigma.
And what's the probability there?
At 5 sigma, the probability that the result is due to random chance drops to less than 1 in 3.5 million.
A huge difference.
A massive difference. So skeptics are correct to point out that the K2-18b DMS detection is not statistically significant nor robust because it falls well short of that crucial 5 sigma threshold. It demands confirmation through future observations.
So we are perpetually stuck in this fascinating purgatory. We get these incredibly exciting hints, but never the definitive yes.
And that constant ambiguity leads us right back to the stark question of the Fermi paradox.
It's great silence.
Right. And the Fermi paradox is really the ultimate existential driver for this whole multiplanetary vision. Musk has been very explicit about this. He believes there's a good chance that there's simple life on additional planets, but he remains deeply skeptical about additional intelligent life in the known universe.
And he backs up that skepticism with some very current empirical evidence from his unique perspective in low Earth orbit, right?
Yes, he used the sheer scale of his Starlink constellation as a kind of proof. He says with roughly 6,000 Starlink satellites orbiting Earth, providing this unparalleled orbital coverage, he has seen no evidence for aliens. He says he has not once had to maneuver around a UFO.
He wants rigorous evidence, not just a fuzzy blob.
Exactly. And that real-world, highly skeptical stance on intelligence being common, it leads to a fierce philosophical requirement.
The scarcity mindset.
It dictates a fierce scarcity mindset. If the universe is huge and time is vast, and yet we are still asking, where is everybody? Then the intelligence, the consciousness that we possess must be incredibly rare.
It's like a tiny candle in a vast darkness.
And if that candle is unique, or even is exceedingly rare, then its preservation becomes the absolute imperative. It overshadows all other goals.
So the entire endeavor shifts. It's not about exploration anymore. It's about existential preservation.
Right. If we are that rare, then being confined to a single planetary cradle means we are susceptible to certain extinction. And the survival of that rare candle of consciousness necessitates establishing a self-sustaining, multi-planetary civilization. That urgency is what makes the project so intense.
Which brings us to the human imperative. This drive to Mars, it isn't a typical corporate or government objective. It's the ultimate insurance policy, and it's rooted in that philosophical necessity we just outlined.
That's absolutely right. The core unifying mission across Musk's companies, SpaceX, Tesla, SolarCity, is to reduce the risk of human extinction by making life multiplanetary.
He frames it as a moral duty.
A duty to maintain the light of consciousness to make sure it continues into the future.
So let's consider the two types of catastrophes that would necessitate such an extreme action, starting with the certainties.
The certainties are tied to the clockwork of stellar evolution. Our sun is in its prime right now, but in 5 to 10 billion years, it's going to swell into a red giant. It will sterilize Earth and possibly even engulf it.
That seems very far away.
It is, but the sun's luminosity will increase dramatically long before that. It will likely render Earth uninhabitable for complex life in under 1 billion years. That's a slow-motion disaster that we simply cannot stop.
But the more immediate driver, the thing that explains the aggressive timeline, is the risk of black swans.
Black swans are the unpredictable, low-probability, high-impact events. A civilization-ending asteroid impact, a global pandemic far, far worse than anything we've experienced, nuclear war, or even, an unmanageable AI catastrophe.
And if humanity remains confined to a single planet.
A single one of those events guarantees the end of consciousness. Moving off Earth is just following life's most fundamental impulse: diversification and dispersal in the face of existential risk.
So the goal isn't just to visit Mars, it's to establish a true redundancy, a self-sustaining colony within about 30 years.
A colony capable of surviving even if all resupply and communication from Earth were to suddenly cease.
But to achieve a goal of that magnitude, you have to throw out all the conventional wisdom. Which brings us to his defining methodology.
The first principles, philosophy.
Right.
The methodology that underpins everything he does, from rockets to electric cars, is this first principles thinking, or what some people call zero-based design.
Which means what, exactly?
It means breaking down a problem to its absolute fundamental truths, the physics of it, and then building your reasoning back up from that foundation.
This is in direct opposition to thinking by convention or analogy to prior experiences, which is where innovation so often stagnates.
Because when you think by analogy, you accept the existing price structure, the existing limitations. You fall back on that dreadful phrase, "It was the standard way things had always been done."
And the SpaceX origin story is the perfect example of deconstructing those assumptions.
It is. He wanted to send a small greenhouse to Mars, the Mars Oasis, just to keep the idea of Mars in the public consciousness.
Yeah.
He went to NASA's website looking for plans, and he found nothing.
And he realized the problem wasn't the technology, it was the cost.
The costs were astronomical, enough to break the NASA budget, as he calculated it. The core assumption was that rockets must be expensive.
But he broke that down.
He did. He realized the materials themselves, the aluminum alloys, carbon fiber, titanium, they were actually cheap. The cost was inflated by the supply chain, the bureaucracy, the legacy processes.
So when he failed to buy refurbished Russian ballistic missiles because the seller kept raising the price.
And scoff at him, yes. He decided the only way to fundamentally reduce the cost was to build the rockets himself, for the very first principle.
And we see this zero-based design applied across all its technological ventures. Tell us about the engineering example, the one involving 100,000 GPUs.
Ah, yes. The challenge of building massive computing clusters for training large-scale AI models. Instead of relying on established data center architecture, they broke the problem down to its simplest components.
Forget the traditional data center shell.
Right. Focus on the core needs. The building itself, the immense electrical power, the cooling for 100,000 hot chips, and critically, power smoothing.
Power smoothing sounds deceptively simple, but it's critical for coherent training, isn't it?
It's everything. When 100,000 GPUs all ramp up at the exact same moment, the power demand fluctuates wildly. The standard utility grid can't handle that instantaneous variation.
So what was the first principles solution?
It was to combine and modify the software of Tesla Megapacks, these are massive battery storage units, to absorb and instantaneously supply those power variations. They essentially act as a huge buffer. This eliminated the need for specialized, multi-million-dollar industrial power management systems.
And even in his very first software venture, Zip2, the philosophy held.
It did. Back in 1995, the fundamental problem wasn't how do we build a website. The problem was that small businesses had no online visibility because they didn't understand the internet.
So the solution was a searchable directory tied to maps. It solved the simple core problem without being constrained by the old Yellow Pages model.
Exactly. It's a philosophy built on ruthlessness and a relentless focus, which of course takes a massive toll on the working environment.
Yes, achieving these revolutions requires an almost unbelievable level of intensity. It leads to what employees call Musk land.
And his first wife famously described him as the Terminator, a person who locks his gaze onto something and says, "It shall be mine."
That approach is driven by strategy and intellect, and it must create a highly charged atmosphere.
Extremely. Employees learn very quickly that the word no does not exist for him, not because he's irrational, but because he believes any perceived roadblock can and must be deconstructed using first principles until a solution emerges.
The human cost of that intensity is high. We hear reports of 90-plus hour work weeks, people quitting within months because of the pace.
It's a high burn rate environment. And it's fueled by his deep-seated conviction that the stakes are existential. If you make a mistake that slows down the path to Mars, in his mind, you are actively hindering the survival of consciousness.
And that sense of duty manifests as extremely direct, often harsh criticism.
It does. I read one quote that the kiss of death was proving Elon wrong about something. Is that true? Or is that just part of the legend?
Anecdotally, it seems to be true, though it's not always literal termination. He's described as having a very low tolerance for people who rely on conventional wisdom or who just can't keep up with his pace of thought.
So he would fire or marginalize those who couldn't handle his direct style?
Or who resisted the first principles approach, sometimes even if they were proven right but wasted time getting there. The key is execution speed. One engineer recalled him saying, "What we have to do is fucking hard and half-assing things won't be tolerated." It's fascinating because the end goal is, in a sense, altruistic saving consciousness, but the means are often incredibly demanding and personal.
And that relentless energy is precisely what made Hollywood figures like Robert Downey Jr. draw inspiration from his persona for Tony Stark.
Right.
Downey Jr. saw Musk as a contemporary of Stark. He saw that blend of engineering genius, eccentric ambition, and a total willingness to operate outside conventional norms. It's the ultimate Iron Man personality.
Fueled by an unshakable belief in the technical solution, even if it requires emotional distance or personal sacrifice.
And that drive ultimately manifested in the colossal hardware needed for the mission. Starship.
So we've established the philosophical necessity. Now we turn to the physical mechanism for getting us to Mars. And the Starship architecture isn't just about building the biggest rocket. It's about creating a fundamentally new economic model for space travel.
The financial genius behind Starship is that decision to create one integrated system that replaces SpaceX's 3 existing and highly successful profit centers.
The Falcon 9, the Falcon Heavy, and the Dragon capsule.
All of them. Musk calls this cannibalizing their own current product line.
Which sounds completely counterintuitive for a business focused on growth. Why make your own best-selling products obsolete?
Because the goal is not profit optimization. The goal is Mars. By combining all of their current engineering talent and capital resources into a single program, Starship, they focus all their effort on the one thing that gets them there.
And that massive internal allocation of resources is crucial because it keeps the company privately owned.
Exactly. It insulates them from public market pressures that would demand short-term returns over these long-term existential goals.
Okay, let's talk scale, because Starship is truly immense.
The ship stands about 48 meters tall with a 9-meter diameter. It's just vast compared to any traditional capsule.
The payload capacity is what, 150 tons?
Max ascent payload to low Earth orbit is 150 tons, yes. It provides unparalleled capacity. And that large fairing size fundamentally changes what we can do in space.
For instance, not just collecting space debris, but building telescopes far larger than anything we currently have.
You could house a Hubble-style mirror with 10 times the surface area, or deploy massive next-generation deep space probes. But for the crew configuration, the pressurized volume is 825 cubic meters.
Which is significantly greater than the cabin volume of a modern A380 airliner.
It is. And that's essential for keeping a large crew sane and productive during the long transit to Mars.
So what does that transit configuration look like?
For the 3 to 6 month trip, the configuration includes 40 cabins, central storage, a galley, and a shielded core area designed as a solar storm shelter. The capacity is typically around 100 people per flight.
And that scale is the first principle applied to colonization.
It is. You need mass, and you need people arriving quickly to establish a viable, self-sustaining population, not just a small scientific outpost.
And that kind of scale requires extreme cost reduction, which brings us to the two pillars of Starship's efficiency: full reusability and the methane economy.
Methane, Texto-4, and oxygen, Tecto-2, are the propellants of choice, but they're used in a specific state, subcooled.
Okay, why go through the extra complexity of cryogenic cooling? What's the benefit of subcooling?
By cooling the propellants well below their standard boiling points, they become much denser. This subcooling increases the density by a crucial 10 to 12%.
And that seemingly small gain.
It translates to a significant increase in payload capacity and range. It maximizes the amount of mass you can get to orbit per launch. And of course, methane itself is intrinsically low cost, which further slashes operational expenses.
The engine powering all this is the Raptor. The design must be revolutionary to support full reusability and these high thrust-to-weight ratios.
It is. The Raptor is designed to be the highest thrust-to-weight engine ever made. It uses what's called a full-flow staged combustion cycle.
Which is a crucial technical detail.
It is. Most rocket engines use a small portion of the propellant just to drive the turbopumps, which means they lose some efficiency. The full flow cycle ensures that all the propellant flows through the combustion chamber, maximizing efficiency and generating incredible thrust.
And that high performance is mandatory for the propulsive landing.
For high reliability propulsive landing, yes. The Falcon 9 proved the methodology works. But Starship is designed for multi-engine out capability.
It's the transition from experimental to reliable.
That's the goal. Far more redundancy, aiming to achieve landing reliability comparable to the safest commercial airliners. It's an unprecedented goal for a rocket.
And the ultimate game changer is ISRU, in situ resource utilization. This is what makes the round trip feasible. Tell us about the Sabatier process on Mars.
ISRU is the true first principle of Martian colonization. It has to be. On Mars, the Starship must be refilled for the return journey using local indigenous resources.
And this is done via the Sabatier process.
Right. You take Martian atmospheric carbon dioxide, TextCO2, and you combine it with hydrogen, which you extract from local water ice.
So what's the chemistry there?
You combine the TextCO to the hydrogen, and the process yields methane, TextEJEHH1 hard noble. That's your rocket fuel and water, TextEAJ. And that water can then be electrolyzed to yield more oxygen for the oxidizer and more hydrogen to continue the cycle.
And since Mars has much lower gravity than Earth,
the ship can launch directly from the surface using the propellants created right there. It eliminates the need to haul all the return fuel all the way from Earth.
It's an incredibly elegant solution, but it relies entirely on a massive functional industrial system operating on the surface of another planet.
And the challenges are immense. They are compounded by the 26-month spacing of the Earth-Mars launch opportunities. Every error, every missed deadline results in a 2-year delay for the next attempt.
Let's start with the most critical foundational element for ISRU, the text-to location problem.
To produce the roughly 2,400 metric tons of propellant, you'd need for just 2 crewed Starships to fly home. You need a substantial, accessible water source right at the landing site.
Which forces a trade-off. Where is the water, and where is the best place to land?
And why do those location preferences matter so much?
Well, missions generally prefer equatorial regions. Launching from the equator provides a velocity boost from the planet's rotation, which minimizes the total launch energy, the delta V required to get into orbit or return to Earth.
But current observations suggest that the widespread subsurface ice deposits. They're primarily located at the mid-latitudes, from 30 to 60 degrees, not in the preferred equatorial regions.
So there's a disconnect. The engineering prefers the equator, but the resources might be much further north or south.
Exactly. And to make it worse, the instrumentation we currently use, mostly ground-penetrating radar from orbit, is poorly suited to explore deposits deep enough to be sheltered from sublimation.
So the interpretations about water availability are subjective.
They are, which means massive prospecting and validation efforts have to be conducted in situ, on the ground, before a landing site can be finalized.
Given that reliance on water and all the necessary R&D on the surface, the timeline has drawn significant criticism.
Experts are very clear on this. The current, very aggressive timeline is seen as unachievable. They estimate that developing and validating the critical elements, the automated ISRU plants, the power systems, the life support, that's going to require at least 20 years of iterative development.
Specifically because of those 26-month gaps between opportunities.
You just can't rush the physics of orbital mechanics.
But doesn't that lack of feasibility undermine the urgency that's derived from the whole tiny candle philosophy? If the timeline is impossible, then the existential insurance policy is delayed by decades.
That is the key point of friction. It suggests that the philosophy might be running ahead of the engineering reality. It doesn't undermine the need, but it certainly dictates a level of patience that might clash with the relentless urgency of the builder.
And beyond water and timelines, what are the core technical hurdles for the Starship vehicle itself?
First and foremost, the reusable heat shield. No one has successfully developed a truly reusable orbital heat shield.
All right.
And Mars's atmosphere, while it's thin, is 95% carbon dioxide. When Starship enters at hypersonic speeds, that atmosphere ionizes, creating a plasma with a much higher concentration of free oxygen than Earth's atmosphere has.
And that free oxygen is chemically aggressive.
It will erode traditional shield tiles much, much faster. This makes the reusability challenge even harder on a Mars return than it is on an Earth return. It requires new material science.
Then there's the sheer size of the vehicle during landing.
The 52-meter height of Starship creates a severe stability challenge for a propulsive landing. I mean, imagine balancing a massive pencil on its tip using jets of flame.
NASA traditionally used shorter, broader vehicles with parachutes or airbags.
Exactly. Landing a vehicle that tall requires impeccable control systems and, as we mentioned, guaranteed multi-engine out capability.
And finally, the power system. You can't run an ISRU facility that big on solar panels alone.
No, you can't. Autonomous power systems are mandatory, and they have to be deployed ahead of time. This necessitates nuclear fission power.
So NASA is developing these small, reliable kilopower reactors.
1 to 10 kilowatt systems, or even larger 40 kilowatt systems. These have to be landed autonomously at an earlier opportunity, connected via cable to the main base, and then actively shielded, probably by constructing an earthen berm to protect the eventual crew from direct radiation.
So all of these complex, interconnected systems must be deployed and proven operational over multiple 26-month cycles before a crew can even think about safely arriving.
It is a monumental logistical task.
We've traveled from the ultimate fate of the cosmos, the big crunch, the big rip, the final decay, and we've landed on the most intricate engineering demands of Mars.
And that drive to become multi-planetary is fundamentally driven by that philosophical urgency to protect the scarcity of consciousness, that tiny candle in a vast darkness.
That human response is potent, but it has to be viewed critically. We have to address the perspective of philosophers like Hannah Arendt, who worry deeply about the consequences of this objective perspective that science and space conquest require.
What was her core concern about this rush to the stars?
Arendt feared that by seeing the Earth solely as an object to be conquered or abandoned, this detached scientific view risks alienating humanity from its own earthly roots.
So if we reduce ourselves to mere objects in a fabricated artificial world,
she argued we risk stripping away our fundamental freedom and dignity, that we could lose the meaning in our actions. She urged that our scientific inquiry must remain rooted in a planetary consciousness, in our shared earthly experience.
that's a vital counterpoint to the idea of constantly running away from Earth to this objective, cold, engineered future on Mars.
It is. But Stephen Hawking's final theory offers a beautiful bridge between Arndt's humanist concern and the scientific drive.
How so?
Hawking's top-down cosmology suggests that the laws of physics are not these rigid pre-existing rules. They are patterns that emerge from the universe itself. And crucially, he posited that our inquiries, the very questions we pose, the act of observation, they actively shape the history of the universe.
So that implies that human consciousness is not just a rare passenger, but an active, integral participant in defining what reality is.
It means that if our scientific endeavors are rooted in earthly experience, as aren't wished, but at the same time our conscious investigation defines the cosmic history, then our presence is intrinsically valuable, whether we are on Earth or on Mars.
And Musk's stated goal for SpaceX really encapsulates this synthesis,
What's that?
the expansion of consciousness to the stars, so that we may understand what questions to ask about the answer that is the universe.
So if the universe's history is defined by the questions we pose, questions of fate, of life elsewhere, of our own survival, and if our civilization is that tiny candle tasked with asking them, what great question born of this deep dive into cosmic collapse, alien silence, and human ambition will you pursue next?
Thank you for joining us for the deep dive.